Okay, so let's talk about one of the toughest puzzles in modern medicine, amyotrophic lateral sclerosis, or as most people know it, ALS. It's a truly devastating disease that piece by piece just disconnects a person's brain from their own body. But how? How does that actually happen? Well, to really get it, we've got to go on a journey. We're going to peel back the layers, starting right at the bedside with the patient, and drill all the way down to a single, tiny protein that's gone rogue. This is the story of how we're unlocking ALS, from the patient right down to the protein.
So here's our game plan. First, we'll look at the clinical picture of ALS. Then we're going to zero in on the main culprit, this thing called TDP-43 proteinopathy. After that, we'll trace the cascade of damage it causes, talk about a really cool new discovery, the methylation break, and finally, we'll explore the new frontiers in treatment that all this science is leading to. Let's dive in. All right, so every investigation has to start somewhere. For ALS, that starting point is in the clinic, with the patient. So how does this disease first make itself known?
So, ALS typically shows up in one of two main ways. For the majority, around 70 to 75% of people, it starts in a limb. You know, they might notice some weakness, cramps, or twitching in a hand, or maybe their foot starts to drop. That's what we call limb-onset ALS. But for the other 25 to 30%, it starts in the face and throat. We're talking slurred speech or trouble swallowing. That's called bulbar onset, and honestly, it often comes with a tougher prognosis. Why? Because it hits those critical functions like breathing and eating much earlier on. But here's the thing, it doesn't really matter where the symptoms start, in a hand or in the throat. The core problem, the real tragedy of the disease, is exactly the same. It's the selective death of our motor neurons. Think of these neurons as the electrical wiring that connects your brain's commands to your muscles. In ALS, that wiring gets cut. The signals just can't get through anymore. And when the muscles stop getting those signals, they waste away. Okay, so the big question is always, is it genetic? Well, for a small slice of the pie, yeah. About 5 to 10% of cases are what we call familial. They're passed down in families because of a known gene mutation. But, and this is a huge but, for the vast majority, we're talking 90 to 95% of people, ALS just seems to appear out of nowhere. There's no family history. That's sporadic ALS, and it's a much tougher nut to crack. Probably some complex mix of genes and environment that we're still racing to figure out. And this is the number that really puts everything into perspective. 2 to 5 years. That's the median survival time from when symptoms first appear. That's it. It's an absolutely brutal and rapid progression, and it's exactly why researchers are working around the clock. Every single clue, every tiny discovery is just so critical. So, if it's not a clear-cut genetic story for most people, then what is the biological smoking gun, right? To find that, we have to zoom in. We're leaving the clinic now and heading to the microscope to identify our number one suspect. And this leads us to the absolute key question. I mean, think about it. What single unifying problem could possibly connect 97% of all ALS cases? We're talking sporadic, familial, all of them. If we can find that one common thread, well, maybe, just maybe, that's where we can intervene. And here it is. The answer is a protein called TDP-43. In an absolutely staggering 97% of all ALS patients, this one protein is the problem. It goes rogue. This isn't just a feature of the disease. It is the central unifying feature. Seriously, understanding what TDP-43 is, what its normal job is, and how it all goes so wrong, that is the key to this whole puzzle. So where does this protein even come from? Well, like every protein, it has a genetic blueprint. For TDP-43, that blueprint is a gene called TARDBP, which lives on chromosome 1. This gene provides the instructions for making a protein that our neurons absolutely need to survive. But here's the kicker. In most ALS cases, the blueprint itself is perfectly fine. The problem isn't the instructions, it's what happens to the protein after it's made. Something about its behavior goes haywire. Okay, so now let's dig into the details of this cellular crime scene. How does a protein that's supposed to be one of the good guys, a protein that's essential for life, suddenly turn into the main villain? It's not one single event, it's a whole cascade of damage, one step leading to the next. So picture this. TDP-43 is like a super important manager, and its office is the cell's nucleus. Step 1, the manager leaves the office. It gets shuttled out onto the main factory floor, the cytoplasm, and for some reason, it can't get back in. That's a huge problem, which leads to step 2, a loss of function. With the manager gone from the office,
All its critical paperwork, which is managing RNA, just piles up. Chaos. And then, step 3, while it's stranded out on the factory floor, this lost manager starts to get into trouble. It misfolds and clumps together with other lost managers, forming these sticky, toxic gunk piles that basically clog up the whole factory.
So this is really a double whammy for the neuron. You've got the toxic clumps gumming up the works in the cytoplasm, sure, but the fact that TDP-43 is missing from its post inside the nucleus is just as bad, if not worse. See, without it, the cell messes up the instructions for 2 absolutely vital proteins. First, STMN2 or Stathmin2. You can think of this as the neuron's repair crew for its main communication cable, the axon. No Stathmin2, no repairs. Then there's UNC13A, which is essential for communication at the synapse, the junction point between neurons. No UNC13A, the signal stops. So the neuron is totally crippled. It can't fix itself and it can't talk to its neighbors.
Okay, so scientists have known about this toxic clumping for years, but just recently there's been a breakthrough. A huge new clue has emerged that might point to a kind of master switch that controls this whole aggregation process. And here it is. This quote from a paper in Cell Reports really sums up why this is such a game changer. What they found is that there are 2 opposing chemical modifications, or tags, that get stuck onto the TDP-43 protein. And these 2 tags are basically in a constant tug of war. One pushes it to clump up, and the other one stops it. They're calling it a methylation break, and this discovery is absolutely massive. It's opened up a whole new way of thinking about therapies, because if we can control that break, well, maybe we can stop the disaster before it starts. Let's break that down, because it's a really elegant idea. Think of it like a car. On one side, you have this process called phosphorylation. That's the accelerator. It pushes TDP-43 to aggregate, to form those toxic clumps. But on the other side, you have this methylation brake. When that brake is applied, it literally stops the aggregation in its tracks. And just like that, a brand new therapeutic strategy snaps into focus. Find a drug that can take the foot off the accelerator and slam on the methylation brake.
Okay, so we've got this incredibly detailed picture of what's going wrong at the molecular level. The big question now is, what do we do with that information? How are scientists turning all this knowledge into actual next-generation therapies? Let's take a look at what's on the horizon.
So check this out. This is a really cool, cutting-edge idea. Inside our cells, proteins like TDP-43 don't just float around randomly. They often come together in these little liquid-like droplets called condensates to get their work done efficiently. Think of them like temporary pop-up offices. In a healthy neuron, these are fluid, but in ALS, it seems like these liquid droplets harden into a solid, toxic state. So what if, instead of trying to blow up the protein, you could just find a way to keep it in its healthy, liquid form? That's the whole idea behind these things called condensate modulators, or CMODs. It's about restoring normal behavior, not just destruction.
And this has led to a bunch of really fascinating strategies being developed right now. First up, you've got companies like DuPont Therapeutics, and they're all in on those condensate modulators we were just talking about. Then there's a totally different approach, targeting ion channels. The idea here is that motor neurons in ALS patients are hyper-excitable. They're firing way too much. So this strategy aims to just calm them down. And then there's this third one, which is just brilliant. Companies like Alchemab and Eli Lilly are looking at people who have the high-risk genes for ALS but somehow stay healthy. They're trying to find what's protecting these resilient individuals, maybe some unique antibodies, and then turn that discovery into a therapy for everyone else. Super clever stuff.
So, there you have it. We've gone from the very first symptoms a patient might feel all the way down to the intricate dance of molecules inside a single neuron. The instruction manual for how ALS works is getting clearer every single day. We know the main culprit, we understand the cascade of damage, and now we have these incredible new clues, like the methylation brake, and a whole new toolkit of potential therapies. Really, the question is starting to shift. It's not so much if we can fight this disease anymore. It's which one of these new keys, or maybe a combination of them, is finally going to be the one that unlocks the cure.
And I like you by my side.